geometry of turbulence and the Navier-Stokes equations.
Если обязательно так делать, можно.
Главное, чтобы эта штука болталась.
А вот это?
Ну да, вот это. Это неудобно.
Вот это?
Да.
О, заодно поправился. Так. Ну, я начинаю, да? Okay. Good evening. I will present you some point of view on turbulence, and it will be only about geometry that related or associated with turbulence notion. And maybe I touch also Navier-Stokes equations, but to do it in details, I will need not only geometry of turbulence, I will need thermodynamics of turbulence. And it will take maybe next time when I will present you complete version of Navier-Stokes. Okay. First, just the standard scheme how to construct Navier-Stokes equation. We start with a manifold, oriented manifold, with Riemannian structure. And after more or less standard geometrical manipulations, we can get Navier-Stokes equations. So the first Navier-Stokes equation itself, it's just simply second Newton law, where mass multiplied on acceleration equals force. And to define acceleration, if you have some flow on or vector field on M, you should differentiate this vector field in covariant way with respect to itself. Okay, and it was my problem. So how to get G, really, if you want to describe some real system. So should we use G that just given by our image, what means the geometry said on our space-time, or our geometry on the Earth, or on this flat, just geometry on this room. But from the other side, when we define Navier-Stokes, we essentially use structure of this substance that will be moved on manifold M. And what I want to show you that really this letter G also depends on some structure on our manifold. And this is what I will call turbulent structure or random vector field or something like this. Okay, so, but I will do step by step. So first, I presented when we talk. I presented thermodynamics, and I used some probabilistic method to get all these laws in thermodynamics. And now I will repeat a little beginning, and then we'll talk about our problem. So the plan will be the following. First, it will be random vectors. The second, it will be random vector fields. Oh, this is really what means turbulence. And the third, it will be geometry of turbulence. So really from this you will get what I have explained.
What language do you use?
Yeah. Sorry. Okay. So first of all, let's go to school, and I will remind you what means random vector. So we have some probabilistic space, so some topological space, not important, with a probabilistic measure, and you have mapping from this space to some vector space V. It will be finite dimensional space, say dimension n.
This is a vector space.
It's a vector space, yeah. It's a vector space. And what we know also from very beginning of probability theory, it's when you have such situation, you can take expectation of x with respect to this measure mu. So it's just simply integral of x and this expectation, it depends on your point of view. You can think that it's result of it's a result of measurement or observation of random vector, or if you wish, you can say that this is not a result, but it's result of activity of some higher forces that can produce from random stuff something not random. Okay, so now I will put another question. So let's take a vector in this vector space, and let's see. Can I get this vector by expectation of the random vector x, but with respect to another measure, not mu? So it's easy to play with this x and to get that it simply will be 0. So I will consider this centered pair. So expectation of x with respect to this measure, it will be just simply 0. Now the question, so is it possible to find another measure? I will denote this mu lambda. It's simply not lambda. It will be, let me be 0, and this will be mu, and this is just proportional to mu 0. So this so-called prior measure, and we're looking for another measure, also another probability law, that expectation or result observation of x with respect to this measure give us vector v. So this is our. So first of all, it's not clear does such a measure exist, and the second, if it exists, maybe it's not only one, maybe there are a lot of them. So what we will do, we introduce some notions that called, let me see, Kullback-Leibniz divergence, or information gain, or relative entropy. There are a lot of names for this. I will use notion of information gain, and this is a way of compare two measures, say measure mu and measure mu 0. And it's given by the following formula. So it should be logarithm rho logarithm rho d mu 0. Rho, this is density of this. And this is, it's very similar to, at least on the formal level, just the same integral or the same sum you write when you define entropy. The only, if you have something infinite, without this measure mu 0, you will never get entropy. So to get entropy, you need one measure more of this mu 0, the prior measure. Okay, why? What is the fun with this information gain. First of all, it's non-negative. And the second, it will be equal 0 if and only if mu equal mu 0 almost everywhere. So this is the way of compare two measures, mu and mu 0. So this formula gives us some number, but this number will be non-negative. But the only that we know that if it will be 0, then it means that these two measures simply coincide almost everywhere. Okay. Why I'm telling you this? So here, let's go to this. So this is, we're looking for this measure mu. And say more or less natural to ask when this measure mu will be closer to measure mu 0 as much as possible. And close means this is quasi-distance, because it doesn't satisfy a triangle, so it's not distance on the measures. But anyway, this is a way to compare two measures and see do they coincide or not. Okay, so this will be our problem that we will try to solve. So I will consider this functional. So density rho will put in corresponding this sum of this quasi-distance. And we add to this two conditions. Rho should be, this should be also probability measure. So we should add this condition. This is the first condition. And the second condition, this one. Where is this one? So the mean of our random vector with respect to this new measure should be v.
We fix v.
We fix it. So I am trying to solve this problem. So is it possible for given vector v to find such it's not mu 0 because mu 0 gives us 0 expectation. So to find another measure proportional to mu 0, such that expectation gives us this vector v. So this v given for us, and that's all. Okay, once more, let's go to Barahaken. So we should add here this Lagrange multiplier. So minus lambda 0 and this relation, integral of rho d mu 0 minus 1, and minus lambda integral rho logarithm rho d mu 0 minus v. So this constrains this one and this constrains. So this
no logarithm, simple expectation, no rho multiply, no by rho logarithm rho. No.
What?
Expectation is rho multiply x. There is no logarithm. In condition. It's the condition second. There's no logarithm. Lagrange multiply is on condition.
Yeah, it's constraints, not condition, but
yes, constraint. Yes, constraint. Not no
constraint.
The second constraint. No logarithm. No logarithm. Why there is logarithm?
Ah, okay. So thank you. Right. I'm sorry. Minus v. It's this condition. This or this condition. And here this multiplier, so lambda 0, it's a number, and lambda, it should be dual to this part, so it should be covector. So simply lambda. Okay, so what we should do, we should take variation derivative. So I will skip all these computations. I simply give you answers. So what we will get? The answer will be the following. So first of all, our rho, it will be the following expression: 1 divided by z lambda x lambda x. The second one, it will be what is z lambda? Z lambda, this integral of x lambda x be 0 or omega. Also, I will need two more functions. One function, I will first only one function. It will be simply logarithm of z lambda. So this is what in physics they call partition function. This logarithm of partition functions they call free energy. But we don't have any energy here, so I will not use name energy, but I will use something very similar. I will call this Hamiltonian. It sounds strange that just in linear algebra, practically, I introduce this name Hamiltonian. But we will see that it will, after short time, it will be really Hamiltonian. Okay, so lambda 0, this is 1 minus h lambda. And what else? I think that's all. Yeah. Yeah, and the more important relation. So you can take this expression for z, differentiate, and you will get x multiplied by this one, almost rho. You should multiply and divide by partition functions, and you will get exactly this expression. So this is what we met in thermodynamics. We call, but it's not important, this one. We call equations of state, or state equation. And you see that to find this measure, I need lambda. To find lambda, I should solve this equation and find lambda from this. It is not clear, is it invertible or not invertible? So if you take Gaussian, so second derivatives, so this will be Jacobi matrix of the system, and it should be non-zero expression. I will present this in geometrical form. To make it more visible. So we consider pair. Oh, we consider this picture. So this is V and V star. So here our vectors V, and here our covectors lambda. So this relation gives us some n-dimensional submanifold here. And if you want to find lambda from V, then it should be such a way. So it's not good if it is something like this. So this is n-dimensional manifold L, and because it's derivative graph of differential of H, so this Lagrangian manifold with respect to form d lambda dv, and it's the same happens in thermodynamics when we introduce state equations. State equations also in thermodynamics, they are just Lagrangian manifolds, and similar this. So simply V should be not abstract vector, but the so-called extensive vector in thermodynamics. Okay, and now what about this is information gain, mu lambda, mu 0. It will be the following. You can easily find this. It will be lambda V minus H lambda. Instead of this expression, I will use letter L here and call this Lagrangian function. This is Hamiltonian functions, Lagrangian functions. And this is two relations, if you just write it here. So V, it's H lambda, and lambda, so we have this function H lambda, and another function L. I didn't specify argument. So I will think about L as a functions of V. So, and I think you easily recognize that it's so-called Legendre transformation really between H and L. This is why I used names Hamiltonian and Lagrangian. So they related to each other by Legendre transformation. So this L, this is Lagrangian. It's also information gain. I want to stress that there is no mass, nothing. Just simply probability, maximum of the use of this was information gain. But when we find this formula, these relations, so you can also find the second pair, but it's very easy. Just differentiate, you will get this relation. So this means that if this is manifold diffeomorphic to V and diffeomorphic to V star, then we should require that differential of this map and this map should be let's see, I write here. So this, here lambda equal LV and V equal H lambda. So if you wanted to have the coordinates V here, it's okay, but then this requires that the Hessian of H should be not non-zero. So this is Hessian of H. It should be non-degenerated or regular simply. The same about Hessian of L. And because one of this map is inverse to another map, so it means that these two matrices should be inverse to each other. So he gets Hessian of H, he gets Hessian of L, and just the simply inverse matrices. Okay. So this is, but But how we find these equations? We find the equations simply by taking variational derivative, put it equal 0, and find these relations. But to see what it is it is it minimum, maximum, or simply something not clear? So what happens about this Hessian H and Hessian L? It's once more it's taken from thermodynamic. So you can try to find central moments of this vector x. So I don't need it. No. I simply remove this. This formula for, where is this formula? So if you take one derivative, okay, let me do this. It's not difficult. So if you take derivative, you will get integral, but with different lambda. So you will get x lambda x multiply on x and on v0. So this is how derivative looks like. So, but rho, it's the same exponent, but divided by z lambda. So what I do, I will divide by z lambda and will multiply on z lambda. So this gives me mean value of x. And here I will get, you see, z lambda divided by the derivative z lambda divided by z. It's simply h lambda, right? Derivative of logarithm of z.
Expectation in measure.
Expectation in
Measure
mu lambda. Yeah. So this mu r. So this is the derivative of derivative h lambda give us the first the average of x. If you differentiate once more, you will get 1x here also, and you can check that h lambda it's nothing but the second central moment of x with respect to mu lambda. So it is, you write more correctly. So it will be d2 dh lambda I lambda j d lambda I tensor d lambda j, and this is will be just second central, so sum over ij. So this is show you that the Hessian, okay, Hessian here will be simply matrix, but it's better to say about Hessian, the Hessian is this symmetric true form. So this is symmetric true form with its second central moment. What we know that this is guy, it's non-negative. And more, we know that if you want to estimate errors of your measurement, then you should use it. Okay, this matrix, but not its metric itself, but inverse matrix, as Chebyshev inequality shows that its guy will show you in which interval you expect your random vector. So what I wanted to say that really this is two Hessians that we used here. It's simply some non-negative, let's say positive definite two forms. In another way, this requirement, once more in thermodynamics, it's a requirement of stability of result of our measurement. So this guy and this, they just inverse each other. So both of them should be non-negative, should be positive definite forms. So it means that this picture correct if you will add one more requirement. So Gaussian of H and Gaussian of L, they should positive definite. Then it means that all these equations, they solved, at least locally solved in both directions, and we can express lambda in V or V in lambda, it doesn't matter. But these two functions, I will repeat once more, they just related by Legendre transformation. Exactly the same we meet in classical mechanics. So you have Hamiltonian description of mechanical system, you have Lagrange description, and relation between them also given by Legendre transformation. Okay, and maybe I also just will write this formula for rho, this one, in slightly different way. Let's right here. Rho is 1 divided by z lambda. Z lambda is exp of Hamiltonian, just from this. So it means that I can add Hamiltonian to this, and I will get expression of this form. So rho is an exp of lambda x minus h. It's a very important formula in statistical physics. They get it from some mechanical reasons, but we got it just from this simple list of formula. Okay. Let me see. Okay. So let's go from algebra to geometry. So this is what happens if you just simply measure random vectors or computing the. Yeah, I forgot to say this. The positivity of them means that if you take the second variation of our functional f, you will see that it's positive. It's also very easy to differentiate twice. It will be some this of this in there. So it means that really what we found, this is a minimum. Formally, you can call this as a principle of minimal information gain. I prefer to use another razor. I will use it as the principle of Occam's razor. So we are trying to reduce information that we need to measure our vectors as minimum as possible. Okay. Now let's go to geometry. Really, we will need only this list of formulas. I don't think we will need the rest ones. Okay. So let's consider now manifold M. Then we have tangent bundle over M. And at each point x, we have vector space, namely tangent vector space to M. So if it has dimension n, so this is exactly the situation. How to transform this is procedure of measurement of random vectors to this situation? We use their probability space omega with blah blah blah. Now it's not clear what we can do, because for this point x we have one probability space, for second, for another point another probability space, and so on. So what I will do, I will back to our description when we say random vector. This was this map. And what I will do, first of all, I will take image of this map. So let's denote by D. The second, if you have such map of spaces or sets, then you can measure mu zero from this to this. So I will not say kappa zero. And doesn't matter, it's mu zero or any other measure can be simply moved in on D. So this will be probability measure on D. So I will say that I have random vector if I simply have D inside of the space V, and this space equipped with probability measure kappa. So this is now a random vector for us. So what I will do here, I will take my and so yeah, I remember that really zero inside of D. So just some domain that contains zero and just domain in V. So let's do it at each point. At each point we will take domain dx in the tangent space. It should also zero belongs to this, and some probability measure, say kappa of x. So it's like this. So our M, this is tangent bundle, and this is something here with a name D. And at each point we have this is dx and some probability measure here. So it's very natural to call such situation random vector fields. To be exact, maybe we should require that it depends smoothly in X. It means that if you take, say, smooth vector field and
why don't you want to consider the measure on the whole V?
Because this is procedure, it's give you a measure only on image of X.
Yes, but
yeah, I can put zero, say there.
Well, not to think about these images, just consider it as a measure on V. The measure of some subset of V is the measure of its pre-image in.
So every time after this you should be careful to say what you mean to measure, because this measure from this, how you will extend on the whole space Tx. So we can.
But it will be outside D. It will be zero.
Oh. Okay, but I prefer this picture. Sorry.
You will just not need to care about the G's. But of course, it doesn't change anything principally, but
Anyway, it's a good idea to keep in mind the idea. It's, okay, so this is about our vectors V. This vectors simply in this space. What about lambdas? Lambdas, they should be elements of the dual space, so it should be covectors. So we have something similar here. So once more M. This is cotangent bundle now. And we have the similar picture. I will call this D star. This is the set of all these lambdas that I can get in my picture. So just look at here. So lambda is this derivative of this is function L in V. And so this is that I wrote here. It's simply a set of all possible derivatives. So this point X. Okay. And what means measurement in this situation? So in previous picture, to find V, we should take some lambda and compute this as derivative, and you will get your V. So lambda give us mean value. So what happens here? So lambda now should be, I will write, instead lambda, I will write theta. It should be differential form on M. At each point, I should pick lambda, and this will be simply value of this form. And when I will do this, so I will get vector field. This is...
Можешь сменить обозначение, то что омега была. Нет, давай лямбду большую какую-нибудь.
Let's, from this point, forget about omega. There is no omega for us. So this omega now, I'm sorry. Lambda, it's only for vector spaces. For manifolds, I used omega. I'm sorry, it's common standard notation. So what it means that if you take differential forms, the mean of this differential, the mean of this random vector field, it will be vector field that we should compute it by using this relation. But let's now see. First of all, this function RH, it's now a function on T star. So it should be depends on X. And let's say I will write P instead of lambda. It's also common notation. So and then what I should do, I should take a vector field where VE, it should be DH on DPIs at the point X and theta X. So it will be vector field here, sum of DH DPIs computed at the point X theta X GDEqi. So you recognize here projection of Hamiltonian field on the base. And this is why I prefer to use now, this is name Hamiltonian for function H and Lagrangian for function L, because they really are related by this relation. So you can consider the situation like this. So you have a random vector field. Or maybe you can say that this media is just simply turbulent for us, because at each point you cannot see unique vector. You have random vector at each point x. And now you put differential one form. Once more, from physical point of view, differential one form, this is force field on your manifold. So you take this force field, put it on your manifold, and this is the result. So the only what we should require is that everything here should be smooth. So to be smooth, it's enough to require that this expression will be smooth. So here we should put our measure kappa and require that this expression now should be smooth in E lambda and in x. And not big x, but small x, because it will be at each point x, it will be this function z, it will be now a function z and px. Also h will be also function p and x. So I will require that this function is simply smooth, and they define it by this our new measure. So this means smoothness of this measure. Okay. So this is some realization of the picture. So you have some random media where you cannot measure really tangent vectors. So there is no flows in this sense, because you're not able to measure vectors. It's random at each point. So, but you will remove this randomness, like in the case of simply linear algebra. You can remove this randomness if you just will go to the averages. And then this is vector random, but this average that we got from differential form, it will be just smooth vector field on the manifold. Okay. What else? Yeah, maybe this formula that I wrote here, just compare with definition of our Lagrangian. So it's exactly Lagrangian here. So it means that our form, this density function, is simply exponent of Lagrangian. Okay. I said, yeah, and maybe one more remark. One more remark. So this function L is a function of x and v. So our Lagrangian. And this function, I remind you that it's simply information gain. Now, if you take some path x of t on the manifold M, then you can compute this integral of t0 to t1 L of xt x t dt. And this is information gain along your path. So we used here principle of a camera eraser to get all this stuff. So if you continue to use a camera eraser, you should require that this should be minimal. Okay, you should write Euler Lagrange equation, right? And the second order differential equations on this x. And what you can see that these equations also that we use in mechanics, they also just follows from not Maupertuis principle, but Occam-Razor principle. You can ask what happens where is a mass. Mass hidden in second central moment, really. Okay. Now a little more about this picture. So really, if I remember, it should be something like this: d dt, dl by dx point minus dl dx equals 0, right? So this is second order equation. So if you have equation of the second order, something like this: x 2 points minus a b of x and x point, you can write this as a vector field on tangent bundle. So v eta dxi plus b d xi point d xi. Let's write like this: d okay. Let's use this notation. So anyway, this equation is you can represent as a vector field on the tangent bundle, and in Finsler geometry they use its semi-spray. So in other words, this equation that we get here is just some special second order equation or some special vector field on Tm. Let's call this S. I will need this vector field very soon. Okay. So what we know more about tangent bundle? So Tm. So I will use these coordinates here: xi's, vi's. It's fibrous coordinates.
X dot doesn't equal to v.
Yeah, equal. Sorry. Yeah, x. I think something like this, right?
Yes, and here v.
V, right.
Yes.
Yeah.
That's correct.
Yeah, v point is second derivative. Yeah, this one. So this is what we get from our picture. So if we have this Lagrangian and Hamiltonian, you can write either this vector field on tangent bundle or Hamiltonian vector field on the cotangent bundle. But I will need the second picture. What else? Really, on this manifold, we have a field of operators. I will use letter G. It's operators, so-called operators that define tangent structure. This is nilpotent operator, and it has form. Let me see to be correct. DDI. Okay, some I. So this operator, it's operator that nilpotent. Image of this operator, as you see, is simply vertical vectors. And that's all. And yeah, maybe what interesting, if it applies to this spray, you will get simply a diagonal vector field on Tm. So it's another definition of this guy. What is important for us is the following. So if you take Lie derivative of G along S, let's denote this by, say, K. It's also operator. And if you take the following operator, that PH, it's 1 minus K divided by 2, you will see that this operator gives you splitting of your tangent space to, so this is our tangent bundle. So this is vertical, so this tangent spaces, but vertically. And if you take image of this is projector, so square of PH square, it's simply PH. And if you take image, you will get horizontal distribution on the tangent bundle. So this image of PH. And you know that in this situation, you can construct connection in tangent bundle, but this is distribution will be not linear in fiber, so it will be non-linear.
So this is a projected because of the property of J, yes?
Yeah.
Nilpotency. By the way, you can interpret J in another way if you consider T to be a supermanifold with odd.
It
will be just a nilpotent vector field on this manifold that corresponds to the round differential.
Yeah, but why I mentioned about this, it's the only that this construction, just what we is from these tools that we have in hands, allow us to construct this horizontal distribution. So you can construct a Riemann connection on the tangent bundle. And if you remember, when I begin with the Navier-Stokes equation, I said that we need metric and connection, Levy-Chvile connection, define for us accelerations. So we can try to do here, but it will not help us because, first of all, it will be not affine connection, it will be nonlinear connection. This connection with different names known in Finsler geometry. No, not exactly, they add some more requirement on this function L. They skip all the stuff and simply say that we have only this function. But essentially, it will be first, it will be nonlinear connection. And second, we still have this problem, how we can define, say, elementary volume that very important for construction of Navier-Stokes and stuff like this. So it means that this is the standard method of Finsler geometry doesn't work here, and we need something else. So let's go to this picture. I write. Okay. Yeah. Now I will remove it because I will not need it. Let's go back to our picture. So we have this tangent bundle. What else? So this coordinates here, x, say, and v. Xi's and vi's. Let's look at on this formula that we use it here. We require that this is Hessian should be non-degenerated, namely should be positive defined. So let's write Hessian of Hessian of L. So sum dyi, dyj, and here dyi tensor dyj. So what we know that, at least in our picture, this Hessian of A should be positive. Okay, and we have this operator G. It's not a good idea to remove it. Where is this G, the GDEq dv, right? So it has a joint operator that acts on cotangent bundle, and you should simply change these two. So this is a correctly defined object, because Hessian, to define this as Hessian, we need only a affine connection or simply affine structure of the tangent vector space. Then the Hessian will be defined. And if you will consider diffeomorphism of M, they will produce linear transformation on fibers, so they will send you Hessian to Hessian. So it doesn't depend on coordinates and stuff like this. Okay, so let's. Oh, I forgot name. It's very difficult to me to pronounce this name. Mu taken, M taken, it's
matrix which is defined by the Lagrangian, by
yeah, what I want to say. Mahalanobis, yeah. It's statistician. He worked on a very funny problem. So we have some society, I don't know, say Ukrainian people, and you have some another guy, and you should compare, does he belong to this society or not? And they make some statistical observation. After the statistical observation, estimate by some number and say that they never say that with probability 90%, but for sure this guy just from this society. And he used в основном normal laws or Gaussian laws when this L is simply a quadratic form. And then it will be just, this expression will be exactly that he used it in his investigation. So what I prefer to use this name because all names taken. So this apply this operator to Hessian of L, and what you will get, it will be metric. Okay, I will put G with a letter, with a big L. And this is with the four-long metric. So strictly speaking, it's not metric because this is second derivative. It depends not on the x, it depends on v. If L will be quadratic, then it will be metric. But in general, it's just simply horizontal form on the tangent bundle. And this is a very fun stuff. So this is our tangent bundle. And here we have this is metric. And assume that we have vector field, say, I don't know, W. So this is graph of this vector field section of corresponding W. So you take this form and put it on this graph, and you will get metric here. Let's write it as a GW. So in our situation, we after all this, we came to a very funny picture. So we have something on the tangent bundle, this quadratic form. And every time, if you take some vector field, you will get metric on the base. And it will be Riemann metric because we require that this LVV is just positive definite. Okay. But vector field is not good idea because as we saw from all this stuff that really to get some vector field as a result of observation, you should take differential form, make this procedure, so compute this vector field to be v theta, and you will get I will write here not GV, I will write here G theta. And okay, sorry. It will be V theta. And this will be metric G theta. So this is the situation that we have in hands. You take differential one form, make all these operations, and you will get Riemann structure on your manifold. And in addition, you have also vector field on the base manifold. So when we define Navier-Stokes equations, we start with the flow of the manifold. We say flow of the manifold is a vector field. Now we should change our point of view and say that, okay, we have random vector field, and we have this differential form theta. Differential form theta produce average, this is V theta, and produce also quadratic form G theta. So everything what we need in this picture is only differential forms, one form. Differential one forms and necessary pair metric on manifold and vector field on manifold we will get. So now that means that Navier-Stokes equation should be written not for vector fields, but for differential one forms. Okay. I prepare some funny example of all this stuff.
So physically, what does this mean? Traditional Navier-Stokes is written on the field of velocities. Yes?
Yeah, on manifolds that
now
also
we pass to the dual viewpoint.
Yeah.
And who are these forms physically? They should have some meaning.
No, but this is just it's generating forms. So they generate everything. They generate vector fields. That because this is not arbitrary vector fields. This is averages of this random. So it means that this is construction lists us all possible averages on the one hand, and on the other hand, it's also give us all necessary Riemann structures.
And the only thing on which the resulting equation will depend is the initial measure. Yes.
Yeah, prior measure.
Yes. This,
yeah.
This mu zero
yeah,
defines
this is
everything.
Not everything, but practically all what we need.
Well, let's see the example.
Just I will give you example. It's a very fun example. It's the case when we have ideal gas. Not real, but ideal. Okay, I will remove this. So first of all, it's so-called Maxwell-Boltzmann distribution. It says that rho is distribution of velocities have I use notations from statistics, so it's like this. So sigma, this is covariance matrix, sigma v on v. So it's the function rho is given by I don't know, by experimental observation or simply
That of sigma. That of what?
Of sigma. Of sigma.
And,
it's it's normal law, but in our case, sigma it's
implies to the power
2 pi and 3.5. 3.5. Sigma it's m divided by k beta t. So this is Maxwell-Boltzmann distribution for ideal gases. M is the mass of particle, T is the temperature. This is Boltzmann constant. So it means that it's really mu0 is here simply hidden. But what we need not really mu0, but we need these functions L and H and H. So L here, it's 1/2, so m divided by 2k beta t, and here v1 square plus v2 square plus v3 square. And so Hamiltonian also just should revert this and write here p instead of. So this is what we get from Maxwell-Boltzmann distribution. For more general, there is so-called Gibbs distribution. So it is you can write it's not only for ideal gas, but for all others. But if you will survive, maybe sometime I will discuss the thermodynamics of turbulences that appears with this, together with all this picture in geometry. And then we'll discuss this more or less. So what is a mu? Oh, so G M. It will be M divided by K beta T, and here dx square, dx1 square, plus dx2 square, plus dx3 square. So this is this Mahalanobis metric, this one.
so it's a genuine metric, not horizontal to form, but
now because it's quadratic, then it's immediately metric on the base. What is the fun here? This letter T. Certainly, you think that it's like standard Euclidean metrics up to multiplier, but multiplier temperature, it's really function. It's not number. So it means when you will compute so the first term in this Navier-Stokes, you should differentiate and remember that t is not a number, it's a function. I give you just this gamma for this. They're very interesting. Gamma k I j, it's 1/2. And here the following tk, it's derivative in xk minus ti minus tj.
So you mean that T is a tensor.
Yeah, T is temperature. I can write, if you wish, formula for acceleration, but it's easy to do if you have these gammas. You should take covariant derivative of your vector field and differentiate.
You mean that T is component, well, generates components of Christoffel signals.
Yeah. So it's not flat anymore. It's curved manifold. It's conformed flat, but not. And this is really the more funny thing that I found in all this discussion. So it means that the classical Navier-Stokes equations simply for ideal gas, they're not true. They're not correct.
Subscripts is just derivatives.
Derivatives in the xk, xi, and fj. So, and in classical case, we simply mean that it's zero. And write the standard derivatives instead of covariant derivatives. Okay. Do we have time? Not too much.
Well, like 15 minutes.
Yeah, I will finish. Yeah, I simply want to play a little with this observation. So differential form, this theta, or vector field give us this metric on manifold. So it means that Riemann structure, not just something that you just will take from your textbook. It really depends on media that you have in hands. So this is for ideal gas. Something similar happens because there is also Maxwell-Boltzmann distribution for plasma. It's also similar, but there is some extra term here. It's electric potential there. So is the first question. The second question that we, at the very beginning, we can think about these vector fields that generate no arbitrary form. For example, we want to consider potential vector fields. So it means that we take theta to be differential of some function. Let's give you some of this vector field. Here was differential. And after you should write Navier-Stokes equation for them, but at the very beginning, you over-determine your system. Because once you have vector field that depends on n parameters, now you have vector fields depends on only one parameter. So it give you very strong over-determination. The second, it's also a question about this metric. So this metric can be flat. And this is some extra condition for Navier-Stokes. I will remind that once in my life I used this trick when we consider with Valery Yumagozhin, we consider Khokhlov-Zabolotskoy equation. And this is second order quasi-linear equation. If you take symbol of this, you will get metric. And now you can say, okay, let's consider solutions where this metric, but this metric depends on solution. When this metric, say, will be flat, or Einstein, or something similar. And every time when you put this condition, finally, it was a big surprise for me that when you put this condition together with Хохлов-Заболоцкий equation, you will get very overdetermined system, but its system will be solved. It's every time it's overdetermined, but it's formally integrable, or it's compatible system of equations. So this is the same phenomena here. So you can take like this. It seems that you will get overdetermined. You will get, but for many reasons, it will be compatible systems. What else? Potential after it's flat fall when its curvature equals 0. You can say that you have Einstein when its symmetric will be Einstein, and etc. Or say homogeneous turbulent flows when the symmetric will be just metric on some homogeneous space. So it means that if you have enough symmetries, then you can get everything from these symmetries. Okay. I think it's a good idea to stop here. Maybe one remark. So about Einstein equations. Einstein equations also written for metric. My guess that the metrics also came from some random process in our universe.
Okay, it deserves a special discussion, I think.
Yeah, but it's not about Einstein. But say, if you take, say, weather prediction, we also use it Navier-Stokes there, and they never use it structure of this atmosphere. So for them, you also have not this trivial distribution. A little, you should use not Maxwell-Boltzmann, you should use Gibbs distribution, but you will get something similar for atmosphere. And then it means that equations that I will repeat that Navier-Stokes is simply second Newton law. It's mass multiplied acceleration equal force. And the first term, when you write acceleration, you will get surprise like this for.
Okay, thank you very much indeed. Questions, remarks? Questions and remarks?
Олег, а там же вы остались?
Да, там довольно много живых.
Да?
No question, no remark? Strange.
Thank you for your patience.
Okay, thanks a lot. So we meet in a week again here.